Hello my people. As promised, we're going to start this video off with looking at a 4-petal rose. Remember that when we had r is equal to 4 sine 3 theta, basically we had a 3-petal rose. And it wasn't really 3-petal, it was more 3 visible petals. Because between 0 and 2 pi, remember, it traced through these twice. It went positive, negative, positive, negative, positive, and then negative again. What happens when you carve it up, when you carve up the inputs from 0 to 2 pi into 4 regions rather than 6, is that basically none of them get traced over each other. They all get traced as independent petals just because of the way things line up. So let's go ahead and do this. I went ahead and filled out the table of values, and I know that sine is going to come back to the pole when its angle measurement is 0, pi, 2 pi, 3 pi, 4 pi, basically 0 plus pi n, which means that theta needs to be half that. So basically what happens is you have these boundary lines at 0, pi over 2, pi, and 3 pi over 2, and each of the petals is going to be within those boundaries. And we saw something similar to that with this one, right? Except for instead of every pi over 2, the boundaries that we drew were every pi over 3. Okay, let's go ahead and start. Now you know that it's going to be 0, 0. And at pi over 6, it's going to be approximately 3.5. It's like 3.46 something or other. Okay, so we go 3.5, and then 4, and then 3.5 again. So what happens is this first petal, and actually pi over 12 will give you, pi over 12 sine will look at and see pi over 6. So that's 1/2, and it will actually go through this point right here, 2, right? So if you want to draw those, that'll sort of give you a good indication of the width of the petal, okay? So that's the first one. Now, remember that it has everything to do with on what interval is r going to be positive and negative. So r is positive over here, and we know that r is going to be negative from pi over 2 to pi. So r is negative here. So this next petal is not going to be over here. It's going to be reflected across the pole over here. And let me go ahead and put the points out to 4, and then 3.5, and then 3.5. So basically 0 to pi over 2, and then pi over 2 gives you negative r values in order to get to pi. And then here it's going to be positive values again. Okay, notice that the positive is opposite from the positive on this graph, okay, because that was not the case earlier. So what happens is, you know, it's going to trace out positive values here, and so it comes in, and at pi it starts being positive again, or beyond pi obviously, until you get to 3 pi over 2, and then you enter into another negative interval where the sine values are going to spit out negative values and r is going to become negative. So and so from 0 to 2 pi I have 4 petals, but notice positive is opposite from positive, negative is opposite from negative. And that's why these don't overlap. And so if we look at them side by side, I think that'll be somewhat instructive. Because remember what happens is, you know, you have positive, right? Positive over here. And then, oh, sorry, this is kind of messed up. Kind of does that number. Okay, so you have positive here, you have positive here, and you have positive here, and you have negative here, and negative here. Notice that there's, like, basically in this whole interval, this whole little wedge, there's no graph. In this whole wedge, there's no graph, right? In this whole wedge, there's no graph because what quote unquote should be there has been reflected to the other side. There is no interval over here that behaves the same way. And that's because positive is opposite from positive and negative is opposite from negative. Notice positive opposite from negative, positive opposite from positive. And that is the difference. That's why when this is even, the way that the intervals line up, it's positive opposite from positive, negative opposite from negative. So you see all of the petals between 0 and 2 pi. When it's odd, the way that the circle is carved up, the number of pieces it's carved up into winds up creating a circumstance where they're written right on top of each other. So, alrighty, that's enough with the roses. Let's go ahead and move on to the Lemisons. Okay, and Lemisons is basically just the larger category, which includes, you know, cardioids and looped Lemisons and flat Lemisons and dimpled Lemisons and all sorts of fun stuff like that. But they all have to do, basically, if you're looking at it in terms of Cartesian, it all has to do with the vertical phase shift of a sinusoidal function. And how does that translate onto the polar plane? Okay. Well, let's go ahead and again put our values in here, and thankfully our values are going to serve us well here because there's no coefficient up there to x. It's just straight up, so we're going to get our normal values. They're just going to be tweaked a little bit because of the vertical stretch and the vertical phase shift. So it ought to be relatively straightforward to get this table of values. Just as soon as I can populate it with 4 pi over 3, and 3 pi over 2, and 5 pi over 3, and 7 pi over 4, and 11 pi over 6, and 2 pi. Whew. All right. You plug in 0 in for sine, you're going to get 0. So 3 times 0 is, of course, 0, plus 1 is 1. Let's go with the easy values, and we'll come back and fill in the ones in between. Pi over 2, sine is 1. This becomes 4. At pi, sine is 0. This becomes 1. At 3 pi over 2, sine is negative 1. So that's 1 minus 3, or negative 2. And of course, this returns us to 1 again. At pi over 6, sine is going to be 1/2. Times 3 is 3/2. Plus 1 is 5/2, or 2.5. At pi over 4, sine is root 2 over 2. Root 2 over 2 times 3 is going to be 2.1, and then plus 1 is going to be approximately 3.1. And then, of course, pi over 3, sine of pi over 3 is going to be root 3 over 2, times 3 plus 1 is approximately 3.6. Now, the rest of these, of course, have reference angles that are the same as these. You just have to figure out plus or minus, okay? This is still going to be 3.6 and 3.1 and 2.5. But remember that you have the plus 1. So the decimals are going to be the same, but what happens up front? Because this is going to be, instead of 1 plus 3/2, this is going to be 1 minus 3/2. So you get negative 0.5. This, instead of 1 plus 2.121, is going to be 1 minus that. So it's negative 1.2. Okay. Or sorry, negative 1.1. Okay. Now this one is going to be negative 1.6, and this is again negative 1.6 and negative 1.1 and negative 0.5. Now that's helpful, and we move on to the graph of the Cartesian one. Okay, so let's go ahead and take a look at that. Let's go ahead and scale it up to 4, like we did on the last one. So we'll make every 2 boxes 1 unit, or every box equal to 1/2 of a unit. Nothing happens to the period, so we can go ahead and do it as we normally do it. Not that we really changed that last time anyway. But we also got to remember that there is a vertical phase shift, and so the axis of oscillation is no longer the x-axis, but here at y is equal to 1. And that's why you start out here rather than at the origin. And then at pi over 6, you're going to get 2.5. And then at pi over 4, it's going to be 3.1. We don't really have to do that because that's halfway in between these two. But at pi over 3, you're going to get approximately 3.6, and then 4, and then 3.6, and then down to here. And basically, you know how the symmetry works on these. So that's going to be negative 0.5, and it's going to be negative 2. And this is going to be negative 1.6 and negative 1.6. And basically it winds up doing this number, okay? This is, yeah, okay. So that's easy enough, okay? We know how to do that. That shouldn't be overly tough. 2, 3, 4. Yeah, I missed. That's why. I was wondering what was going on with that. It just didn't look right. Okay, so sorry about that. The bottom one down here is correct. It definitely goes down to negative 2, but that up there was a mistake. Got confused between 4 and 5. Okay, so what happens here? Now notice, just like the last one, every time that this returns to the x-axis, this right here is going to return to the pole. But notice that it basically has a smaller interval in the negative and a larger interval in the positive outputs. Well, that's going to be important, okay? So what happens here is, again, we're going to scale this one the way that we normally do, okay, out to 5. And at 0, we're going to start at 1. And then at pi over 6, we're going to go to 2.5. And then at pi over 4, we're going to go to 3.1. And then at pi over 3, we're going to go to 3.6. And then at pi over 2, we're going to go to 4. Okay, well, there's a certain symmetry about how things sort of come back down on this side. So, of course, at 2 pi over 3, it's going to be 3.6, which is just past 3.5. At 3 pi over 4, it's going to be just past 3. Over here, it's going to be at 2.5, and then it's going to come back to 1 at pi. Okay, then at 7 pi over 6, you're at negative 1/2. Or, sorry, at pi over 6, you're going to be at negative 1.5. Okay, because, I mean, basically what happens is this, sorry, disregard that point right there. This comes around like this. And then it hits here, and just for the briefest moment, it's going to be positive, but then it's going to come through, and it's basically going to start charting a second loop, right? But that second loop is going to be smaller, and it's the negative r values. And so at 5 pi over 4, you're going to get negative 1.1, and then negative 1.6 at pi over 3, and then negative 2, right, at that 3 pi over 2. And, these basically have a very, predictable pattern like this. And these basically loop in. Now, remember when I said that the circle got traced out twice between 0 and 2 pi. What happened is, in moving this up, right, one of those circles got bigger and one of those circles got smaller. Okay, so if we wanted to trace instead, give me another color, r is equal to 3 sine theta, and we'll do it in blue. That's basically here. Okay, instead of 2.5, it's going to be at 1.5. Instead of at 3.1, it's going to be at 2.1. And instead of at 3.6, it's going to be at 2.6. And so basically all of these points along this outer rim are 1 greater than they would have been had it just been a circle. Okay? And so that numerically should make sense to us. So what happens is, as you add 1, the circle that's traced out by positive values gets 1 added to them. And the second circle, which gets traced out by the negative r values from this interval, basically gets smaller because you're adding 1 to those negative r values. And then, of course, if you wanted to make it even bigger, make the shift even larger, this would get smaller again, and this would get bigger again. And you could keep doing that until that smaller one disappears. Now, the moment that that smaller one disappears, that's when we have a 0 of tangency here. And that, of course, is what it's a special limacon called a cardioid. And so a cardioid basically is when its r is equal to a plus a sine theta. An emphasis on the fact that those two are the same value. Okay, because that means that there can be no negative r values, because this is a, and the most negative that this expression can be is negative a. And so basically the best they can do is return you back to 0. And then, of course, as you continue to move this up with greater and greater vertical shifts, basically the 0, it actually doesn't return to the pole, and this basically point starts to pull away. And there are animations online that you can go look at and see that happen. And, you know, it's kind of fun. But in your textbooks, you usually have something like this. Okay? And you basically, everything comes in the form of a plus or minus b cosine theta, or a plus or minus b sine theta. And this is really kind of a thing. But basically, if you look, and you can remember that a over b is less than 1, and a over b is equal to 1, and a over b is between 1 and 2. Who cares, okay? Is it possible to have negative values, negative r values? If yes, it's this one. If no, it's one of these 3. You know, basically, is it possible to have, if it's not possible to have negative r values, do you get a 0 r value? Okay, well, that's a cardioid. And these two, of course, are the answer no to can I have a 0. And it just so happens that this little dimple right here disappears the moment that you have something like r is equal to 6 plus 3 cosine theta. Like the moment that the vertical shift, if you're thinking in terms of Cartesian, is twice as big as the vertical stretch, then the dimple disappears and it becomes what this text calls a convex limacon, but what I've also seen another text called a flat limacon. And that, you know, doesn't matter which one you use, just as long as you know what's going on. Okay, let's go ahead and move on to Lemnas Gates. Okay? Lemnas Gates, fun, fun, fun. Okay. Now, if we're looking at this, we notice that this is going to be basically that in Cartesian, because, you know, y squared is equal to 9 sine 2x if I square both sides. But since that's not a function, we'll look at it like this. Now, what does that look like in Cartesian? Well, let's go ahead and see. Let's go ahead and fill out our table of values. 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. Now, if I plug in 0 into this x, I'm going to get sine of 0. Can I take the square root of that? Sure, it's just 0. Okay, now I'm going to plug in pi over 6. If I plug in pi over 6, sine sees pi over 3, so it's root 3 over 2. Okay, the square root of root 3 over 2 times 3 is approximately 2.8. You know, pick up your calculator and try it out if you don't believe me. Now, pi over 4 Sine is not going to see pi over 4. Sine's going to see pi over 2, and the sine of pi over 2 is 1. Square root of 1 is 1 times 3 is 3. Now, pi over 3, sine is going to see 2 pi over 3. And sine of 2 pi over 3 is the same as sine of pi over 3, which is what you had when you plugged in pi over 6. So you're going to get the same output here. And at pi over 2, sine is going to see pi. Sine of pi is 0, and it returns to 0. Now here's where things get a little bit weird, okay? 2 pi over 3, plug it in, sine sees 4 pi over 3. That's in the third quadrant. Sine is negative in the third quadrant and in the fourth quadrant. Now you can't take the square root of a negative number, so you don't get an output here, you don't get an output here, and you don't get an output here. The next time you get an output is when you return to pi, because sine sees 2 pi, which is of course coterminal with 0, and you get a 0. Now let's go ahead and do the ones on this side. Sorry, it's not 3 pi, it's 5 pi over 4, and 4 pi over 3, and 3 pi over 2, and 5 pi over 3, and okay. Now, I haven't taken the square root when I'm dealing with the r, but because r squared has to be positive, the same thing is true here. If this expression, if a theta value plugged in makes sine 2 theta equal to a negative number, then it can't be equal to r squared, and it errors out just like a negative underneath the radical does up here, okay? So let's go ahead and do this again. This winds up being 2.8, this winds up being 3, this winds up being 2.8, and 0, and 0. Okay, well, what does that look like in terms of sort of the Cartesian plane? Well, we're going to change the scale a little bit here so we can see it a little bit better. But let's go ahead and we're going to go, let's see, we're still going to mark it off like this, but it's not going to be, it's going to be pi over, let's do pi. Let's keep it the same. Pi and 3 pi over 2 and 2 pi and 5 pi over 2, and this is going to be 3 pi. Well, between 0 and pi over 2, we have values, right? We can actually chart those, and we know at pi over 4 it's going to be 3, and at pi over 6 it's going to be 2.8, and so it's going to be, you know, this is 2.66, so it's going to be kind of right there. And so what happens is, and if you wanted to do like pi over 12, which is right here, pi over 12, sine would look like pi over 6, right? So sine of pi over 6 is going to be 1/2, the square root of which is root 2 over 2, and 3 times that is going to be 2.1. So you have it kind of like that. But nothing happens in this interval, and then this interval happens again, okay? And it goes up, and then nothing happens in this interval, and you wind up basically doing that again and again and again. But remember that this was actually related, it actually looks kind of like a rose, right? So it looks kind of like r is equal to 3 sine 2 theta. But, because really it's r is equal to 3 times the square root of sine of 2 theta. So those two ought to be related somehow. This is the Lemnas gate. That right there is going to be the rose. Okay, well, let's actually see what this looks like, and then we'll talk about its relationship to the rose. Okay. What happens here is we have, again, like I said, you can do it at pi over 12 right here, and if you do it at pi over 12, you get 2.1. So at pi over 12, you get 2.1. At pi over at pi over 6, you're going to get 2.8, and then here you're going to get 3. So 2.8, that's 2.5. 2.8 is somewhere right around there. Okay, and so the first, right here. Okay, And then, of course, for, you know, these, oh, sorry, for the values over here, you don't get an R value. So basically, this little loop right here corresponds to this first hump. And then nothing happens over here. Error, 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 error. Until you return here. And again, we wind up with, you know, 2.1 here and 2.1 here and 3 and 2.8. And so what happens here is you get positive values again, and it comes out like this. And that's it. That's a lemnis gate. Okay. Now, the whole relationship to the flower or the rose is like this. Now, again, you'll see something like this in your book, and that's all well and good. Okay. But what we really want is, basically, I want to know this is 4 cosine of 2 theta. That's the rose. This is the related lemnis gate. And the related lemnis gate is this fatter portion right here, right? And the reason why it's fatter is because you're taking the square root of numbers that are between 0 and 1. And when you do that, remember, taking the square root of like 16 makes it smaller, but taking the square root of 1/16 becomes 1/4. It makes it larger. And so basically, for all of these values, these are constantly just being pushed out a little bit, okay? So this point right here gets pushed out to here. This point right here gets pushed out to here. But notice, of course, as you get closer and closer and closer to 1, you know, before you have the times 4, as you get closer and closer to 1, that difference disappears, okay? So basically, a lemnis gate like this is a 4-petal rose where 2 of the petals are sort of like phantoms. They don't exist because imaginary numbers have no place on this plane any more than they do on the Cartesian plane. And that's basically it. So a lemnis gate has a relationship to those roses, but you have to basically take into account the output limitations based upon the squaring, or in the case that the way we did it with the Cartesian, the square rooting. Okay. All right, that brings us to the end of the graphing. In the next video, we will do a little converting back and forth between Cartesian and polar, and then after that, we will get on to finding the derivative in polar, which, as we discussed in class, is basically just a matter of parametricizing the polar equation. But if you have any questions, please do shoot me an email. Bye.